Sampling and its reconstruction. We know that sampling is the process that is used to convert the continuous time signal into discrete time signal. Again, from the discrete time signal, if we apply the uh, level operation, that is level assignment, we can get the, after assigning the level assignment and then converting it as a bits, then we can get the digital signal. Okay, so but in the process of sampling, okay, what should be the sampling frequency? Okay, that means what, when we take the samples, what is the minimum time or maximum time between the samples, so that we can recover the original signal, that is the reconstruction of the signal. Okay, already we know the process of sampling, but in this class we will study about the impact of the sampling frequency. Okay, what should be the sampling frequency, or what should be the time interval between the samples, so that we can easily recover back our original signal. Okay, say there is some signal, okay, it is having the say it's having the frequency, the maximum frequency 10 hertz, for example, I am assuming. Again, I can take the samples. Okay, I can take the samples at a defined interval like this. Now the question here is, what should be the time difference between the samples? Okay, the time difference between the sample is Ts. Okay, time interval between the samples. What is Ts? Time interval between the samples. Okay, again we know that Fs is equal to 1 by Ts. That means what? Sampling frequency. The another name for sampling frequency is number of samples per second. Number of samples per second. Okay, suppose if Ts is less, okay, we'll be getting more number of samples for a given time. Again, the bit rate of the signal will increase. But if Ts is less, for example, okay, again, we may not able to recover back our original signal. Suppose if Ts is very, very less, okay, if you are not taking the samples very closely, again, we cannot easily recover the original shape of the signal. Okay, again, if you take more number of samples, we can easily recover, but the problem here is the bit rate of the signal will increase. Okay, again, if you try to reduce the bit rate by taking the samples with the larger intervals, that means just increasing Ts or otherwise reducing Fs. The problem here is we cannot recover back our original signal. Okay, again, what should be the minimum sampling frequency? Okay, what should be the minimum sampling frequency? Say if you are taking more number of samples, very easily you can recover back. Okay, what is the bottom limit? Okay, for the sampling frequency, that means how many number of minimum samples should be there per second. Okay, that is the sampling theorem. Okay, the sampling frequency should be always greater than or is equal to 2 FM. That means what? Suppose the maximum frequency present in the signal is 10 hertz, then our sampling frequency should be greater than 20 hertz. Sampling frequency should be greater than 20 hertz. That means what? At least what should be the Ts? Okay, the Ts should be less than 1 by 22nd. Okay, the time interval between the samples should be less than 1 by 20 seconds. Okay, 1 by 20 seconds. Okay, if it is not less than 1 by 22nd, okay, in this case, if the time difference between the samples is not less than 1 by 22nd, again, cannot easily recover back this signal. Again, suppose if you are not following this condition, again, the distortion will occur. We cannot recover the original signal. So what will happen? Suppose if Fs is less than 2 FM, okay, if Fs is less than 2 FM, if Fs less than 2 FM, or otherwise what is happening? Ts, okay, Ts is greater than 1 by 2 fm in the other way, again what will happen? Distortion will occur. Distortion will occur. Okay. So again, once if distortion has occurred, again we cannot recover back our original signal. So that's why always at the transmitter side itself, we have to apply the sampling theorem properly. Okay, so now we'll see the definition of sampling theorem. Again, this theorem is with respect to transmitter side. Okay, mathematically, this is the sampling theorem definition, that is Fs greater than 2 Fm. Okay, Fs greater than 2 Fm. But again, slightly they are defined both at input side as well as at the output side. That means at transmitter side and receiver side, the same theorem is defined in different manner with respect to transmitter as well as with respect to receiver. But now with respect to transmitter. Okay, so in the transmitter, we are worried about how to sample. Okay, what should be the timing difference between the samples? Okay, that is our main aim. Okay, again, at the receiver side, once if you are given with the samples, how many samples we have to take to recover back the original signal? Okay, so now we are with respect to transmitter side. That means a band limited signal of finite energy which has no frequency component higher than W hertz. That means what? The maximum frequency in the signal is W. Okay, so the maximum frequency in the signal is W, which has no frequency component higher than W. That means what? The maximum frequency in the signal is W is completely described. Okay, completely we are now at the transmitter side, what we are doing, we are defining the signal with help of samples. Okay, instead of complete signal, continuous waveform, we are describing with the samples. Okay, so can be described by specifying the values of signal at instance of time separated by 1 by 2W seconds. So that means what they are telling, what should be the minimum time between these two samples, that is 1 by 2W. Okay, so as I already told you, that is 1 by 2 FM. Okay, so TS, okay, again, this is the distortion case, but the other way of writing this is TS should be less than 1 by 2 FM. Okay, TS is less than 1 by 2 FM. Okay, so here in this case, TS is less than 1 by 2W. At least the sampling time difference between the samples has to be 1 by 2W seconds. Okay, again, why the concept band limited? Why band limited? Okay, why not simply a signal? Okay, see, again, we are telling that the maximum frequency is W. That means what? Band limited. Okay, we are limiting the frequency content of the signal. Okay, so that's why the signal is called band limited signal, because we are clearly telling the signal is not having any frequency which is greater than W. So that's why this signal is called band limited signal. Okay, again, in future to get the band limited signal, okay, we know that before sampling, okay, we know that before sampling, we always use low pass filter. It is mainly to band limit the signal. Okay, it is mainly to band limit the signal. Okay, because we should know what is the maximum frequency in the signal, then only we can apply the sampling theorem. Okay, again, we may think that okay, the original signal is passed through a low pass filter. Again, we may lose some information. For example, I am having a signal x of t, which is having 100% of information. Okay, again, in this case, say from 0 to 10 hertz, say it is having 95% of the information. Again, from 10 hertz to up to infinite, I do not know, I'm having 5% of the information. Okay, for example, this is the case I am assuming. Okay, I am having a signal. In general, it is having 100% of the information that I am splitting like this. From 0 to 10 hertz, it is having 0 to 10 hertz, it is having 95%. From 10 hertz onwards, it is having 5%. Why? Because suppose if I am directly passing this signal, through sampler. Okay, sampler. Then what I will do from the sampler, again I will try to get the original signal x of t. Okay, in the receiver side. Okay, I am sampling the signal again. At the receiver side, what I will do from the samples, I'll try to get the original signal. Now what will happen? Suppose if you do not know, again, so I say in this case, for example, if you are applying fs is equal to 20 hertz, okay, we are thinking that this is the maximum frequency. Okay, again, most of the information is present here. Okay, now how much percentage of the original signal will be recovered back here? Okay, or otherwise, one more scenario I'm taking sampler, again x of t, low pass filter. Okay, again the low pass filter cutoff frequency is 10 hertz. That means what? It will not allow any signal, any component higher than 10 hertz. That means clearly I will be having only 95% of the information. And I'm doing the sampling, I am getting x of t. Say for example, this is the case 1, this is the case 2. Again, simply the first case may look like it is the better one, but it is not so. The second one is the better case. Why? Because again, we are not following the sampling theorem, because we do not know what is the maximum frequency here. There are some informations that is present from 10 hertz onwards. Without knowing that we are operating here, so what will happen? That 5% of the information will collapse another 5% of the information. Okay, so that here we can get only up to 90% of the information, because we are not applying the sampling theorem properly. Okay, if you do not apply the sampling theorem properly, the again distortion will happen. Okay, so uh, so again we cannot recover the original shape of the signal properly. So we may lose more than 10% of the signal here, but in this case we are following the sampling theorem properly, so that we can get this 95% of the information directly, very easily. So that's why whenever you see the sampler, always there will be a low pass filter. Okay, again, the name of the low pass filter is called anti-aliasing filter. The name of the low pass filter is called anti-aliasing filter. Okay, again, what is aliasing? The operation of distortion. Okay, the operation of distortion is called aliasing. Distortion is called aliasing. Okay, again, we know when the distortion will happen. If you are not following the sampling theorem properly, the distortion will happen. That is called as aliasing. Okay, to overcome the aliasing, we are using low pass filter before sampling. That's why this low pass filter is called anti-aliasing filter. Okay, so now next definition with respect to receiver. Okay, at the transmitter side, we have represented the signal with the help of samples. Okay, again, once if you are given with the samples, how to recover the original signal? Okay, in order to recover the original signal properly, at what rate the samples should have been defined? Okay, see, that is the definition with respect to receiver. Suppose a band limited signal of finite energy, which has no frequency component higher than WHz, may be completely recovered from the knowledge of samples taken at the rate of 2W samples per second. So what they are telling, if there are 2W samples, okay, see, W and FM will be using interchangeably. Okay, so if there are 2W samples per second, then only I can recover back my original signal. That means what? At least the sampling frequency at the transmitter side, they should have used at least minimum 2 FM. That means 2W, or otherwise it can also be greater than 2 FM. Okay, then the reverse side with respect to time, what should be the maximum time difference between the samples? That is 1 by 2 FM, or otherwise it can be lesser than that also. Okay, so if you follow this condition, then only we can recover back our original signal. Okay, so next, sampling theorem proof. Okay, we know that x of t is the original signal. Then xs of t, we'll call it as a sampled signal. sampled signal. Okay, then how to get xs of t from x of t mathematically? That means x of t, if you multiply it with the pulse train, we can get a sampled version of the signal. Say, for example, we are having x of t like this. Okay, this is x of t. Again, pulse train is like this, p of t. Again, what should be the pulse train timing? Okay, with the interval of ts. Okay. Then once if you multiply these two, okay, we'll be getting samples like this. Okay, so to get the sampled version of the signal from the original signal has to be multiplied with the pulse train. Okay, we know that the pulse train mathematically can be written like this. Okay, pulse train is equal to summation n minus infinite to plus infinite del of t minus n ts. Okay, at t is equal to 0, this is the impulse. Okay, when you put n is equal to 1, right shift by ts. When you put n is equal to 2, right shift by 2ts. Similarly, left side also, when you put n is equal to minus 1, left side by ts. When you put n is equal to minus 2, left side by 2ts. Okay, so pt can be mathematically represented like this. Okay, from this xs of t, okay, the sampled version of the signal xs of t is equal to x of t multiplied with p of t. X of t, what is p of t? Summation n minus infinite to plus infinite del of t minus n ts. Okay, so now we know the time domain representation. Then from this, how to find out the frequency domain representation? That means what will happen to the spectrum of the sampled signal? Okay, see, next what we are interested is, if I am having x of t, okay, signal in time domain, some random signal, then its frequency domain representation, say for example, it is like this. Okay, with some minimum and maximum frequency. Again, the maximum frequency here is omega m, but once if you go to high frequency from the low frequency, the contribution is decreasing. Okay, so this x of omega is the frequency domain representation of the original signal x of t. Now the question is, suppose if the signal is sampled. Okay, the signal is sampled, that means we are taking the samples at a regular interval. Now, what is the spectrum of this sampled signal? That is the question mark. What is the spectrum of the sampled signal? Okay, that means what? We have to take the Fourier transform for this expression, because we need the frequency domain representation of the signal xs of t, so that we have to take the Fourier transform. So we have to apply the Fourier transform property here. So now xs of t is equal to x of t simply multiplied with summation n minus infinite to plus infinite del of t minus nts. Okay, again, there are these two different signal multiplied in time domain. That means what? In frequency domain, it will be like a convolution. So this we can take the Fourier transform in 1 by 2 pi x of omega convolution with summation n minus infinite to plus infinite del of t minus nts. Okay. Yes, one more mistake we made here. For this signal also, we have to take the Fourier transform. Okay, see, for the moment we do not know what is it, so we'll write like Fourier transform of this one. Okay, then this is x of omega. Then what is the Fourier transform of the train of impulses? Okay, train of impulses, that is 2 pi divided by ts. 2 pi by ts summation n minus infinite to plus infinite del of omega minus n omega s. Okay, so now here you have to be a little bit careful because the first function is in terms of x of omega. That means second function also in terms of omega only. Why? Because Fourier transform we can write in terms of omega as well as f also. Okay, in some book, instead of x of omega, they might be using x of f also. That is also possible. Yeah, but here x of we are in omega domain, so here also we have to use omega domain. But when you operate in f domain, you may not be getting this 2 pi. Similarly, when you operate in f domain, that convolution here itself, you may not be getting 2 pi. So you have to be a little bit careful, okay, whenever you are operating with f or omega. Okay, so now these 2 pi will cancel. Okay, finally 1 by ts. Okay, 1 by ts. Again, x of omega convolution with summation n minus infinity to plus infinite del of omega minus n omega s. Okay, so now this is simple convolution formula. Convolution of signal with the impulse, delayed impulse is signal will be delayed by that amount. Okay, so just this will become like 1 by ts summation n minus infinity to plus infinite x of omega minus n omega s. Okay, so this is the uh, frequency domain representation of the sample to signal. Okay, xs omega is equal to 1 by ts summation n minus infinity to plus infinite x of omega minus n omega s. Okay, so again already we know what is x of omega. X of omega is the Fourier transform pair of the original signal before sampling, that is x of t. Okay, for x of t, if you take if you take the Fourier transform, then you will be getting x of omega. Now what is happening? Okay, we just will apply that summation. It would keep this 1 by ts separately. Okay, say so for example, if n is equal to minus 1, again it is w plus omega s. N is equal to 0, simply x of omega. When n is equal to 1, omega minus omega s. Again it is getting extended on both sides. Okay, now what is x of omega? Then what is x of omega minus omega s? That means what x of omega shifted by omega s. Okay, see, first draw the x of omega. Again, x of omega shifted by factor of omega s. That means what? Right shift by the factor of omega s. Now the question is, what is omega s? Again, we know that from our basics, the omega s should be minimum twice the fm at least. Okay, say suppose if it is 0, this is the maximum frequency. Okay, then again by what amount you have to shift this diagram. See, this is your original x of omega. Okay, this is your original x of omega. This you have to shift by the amount of 2fm. Okay, see, if it is fm, again here you'll be having 2fm. So again we'll be drawing like this. Okay, so this is fs, but fs in this case is equal to 2fm. Again, this is 2fs. Similarly, you will be getting copy here also, that is minus fs minus 2fs. Okay, so now this entire representation is the sampled version representation. This is excess of omega. Okay, and this is going on both sides. Okay, so in this case, what is the assumption? Okay, say for example, this we take as a case 1. Okay, in this case, we have assumed that sampling frequency is twice the fm. Okay, sampling frequency fs is equal to 2fm. Okay, sampling frequency fs is equal to twice the fm. Suppose what will happen? Suppose if fs is greater than 2fm, what will happen? Okay, if fs is, see in this case, if you observe clearly, fs is equal to 2fm, fm plus fm. If fs is greater than 2fm, again we'll be getting some gap in between. Okay, so next case 2, fs greater than 2fm. be getting diagram like this. Again, the copy will be going on both sides. Okay, this is 0, Fm minus Fm, Fs. This is Fs plus Fm. This is Fs minus Fm. This is minus Fs minus Fs plus Fm. This is minus Fs minus Fm. Okay, again, what about case 3? Suppose Fs less than 2Fm. That means what? We are not following the sampling theorem. Okay, in this case, not following sampling theorem. What will happen if you try to reduce Fs? Again, these two triangular will overlap with each other. Okay, it will overlap like this. Okay, this is 0. This is Fs. And this is minus Fs. Okay. So because of overlapping, what is happening? Okay, see, Fs is less than 2Fm. Suppose if you have taken the number of samples less than 2Fm at the receiver side, when you try to reconstruct the original signal, what will happen? In the frequency domain, there will be overlapping. Okay, there will be overlapping between the spectrum. Okay. Again, during the process of reconstruction, what we will be using? See, at the receiver side, we'll be getting excess of omega, but what is our aim? From excess of omega, we have to get x of omega, because we are always interested in recovering back the original signal. Again, how to get this? Simply by using low pass filter, we can get that. Okay, pass this signal through low pass filter. Again, the low pass filter range has to be like this. Okay, the low pass filter has to allow from 0 to Fm. Okay, so if you design a low pass filter like this, then once again, if you pass this excess of omega through this low pass filter, again you can recover back your original signal. Again, in this case also, you can easily design a filter. You can put a filter here. You can put a filter here. Again, you can easily recover back your, okay, this is low pass filter. If you pass through low pass filter, again, you can get the original signal. But here, if you see, okay, if you pass this signal, okay, if you pass this signal through low pass filter, again, you cannot completely get the original signal. It is because of this distortion. That means what? You are not able to get the original spectrum. Okay, once if you have a original spectrum, then only you can get the original signal. Okay, so because of this distortion, okay, that means due to the overlapping of high frequency of the uh, high frequency of the first version with the low frequency of the second version. Okay, again, these are all copy only. Because of this collapsing, again, we cannot get the original spectrum, so that we cannot get the original signal. Okay, this process is called distortion or aliasing. Okay, what is aliasing? The process of high frequency component interfering with the low frequency component is called as aliasing. Okay. So in the next class, we will start from the aliasing. Okay, again, how to overcome the aliasing. Again, one more thing here also, here, case 1, case 2 is following the sampling theorem, but we'll be always using the case 2. Okay, very, very important. We'll be always using the case 2. Why? Because if you observe the case 1, here in this case, you have to design a filter strictly like this with a short cutoff. Okay, again, design of filter with a sharp cutoff is very, very difficult. Okay, this filter is called ideal filter. Ideal filter. That means what? If you are using the strict condition, sampling theorem condition, strict condition, okay, you need to have a ideal filter to recover back the original signal. Okay, again, that means what? Practically, we cannot use this condition. Theoretically, it is okay, but practically, we cannot use this condition. Why? Because we need a ideal filter. Again, the design of ideal filter is difficult, but here we do not need a ideal filter. With help of practical filter, we can get this. Okay, we can design a filter like this with a gradual variation. Okay, here there is no sharp cutoff. It is having gradual variation. Why? Because there is a spacing between the spectrum. For that spacing we are using for the roll off. Okay, that means for stop band roll off, so that we can easily recover back our original signal. So even though the case 1 and case 2 is okay with respect to sampling theorem, but practically we can use only the case 2. That means in all practical cases, okay, for a sampling theorem, Fs must be greater than 2Fm. Okay, again, case 3 is not at all allowed. Okay, so in the next class, we'll continue with this. Okay, we'll see in detail about aliasing, then how to overcome the aliasing. Okay, then how to reconstruct the original signal from the spectrum, because I simply told you how to reconstruct x of omega from xx of omega by passing through a low pass filter. Okay, again, we'll see in detail about that with the help of the uh, mathematical formulas. And also, again, what is happening during this process, what is happening in time domain, that also we will see. Okay, thank you.